we see that there are only fixed and limited number of bits, right? So here we are representing like we are using how many bits? 1, 2, 3, 4, 5, 6, 7, 8 for the fraction part, and 3 bit for the exponent part. So 11 bit, right? So let's say I'm having a computing system of 32 bit. That means that I have only 32 bits to distribute between my fraction part and exponent part, right? So only 30. So if I have 32 bit, I distribute that. Okay, I can say that okay, 20 bits towards the MSB side is my fraction part, and rest 12 bit is for exponent part, right? And then someone can say, hey, I want to allocate like 20 bit for the exponent part and 12 bit for the fraction part, right? And they have their own significance. Increasing the number of bits for the fraction will increase the precision to be represented by the number. It means that how accurate, how close we can go to the corresponding real number values. Increase the number of bit patterns in the fraction will increase my preciseness of the values. As you understand from the previous number conversion, that representation of the floating point binary numbers cannot always precisely represents a value in the corresponding value of the decimal, or vice versa. Like you can say that if you are computing a decimal values, it may not be exactly represented in a binary form because of this multiplication of power of 2. Even in the negative domain, it will leave some room of inaccuracy. Okay. However, as you increase the number of the fraction, you can go close and closer to the precisely to the decimal value or real number value we are trying to represent. However, increasing the number of bits in the exponent will increase the range of the representation of the number. Okay. So just imagine, let's say if you are assigning 2 bits for your exponent and 30 bits for your fraction, your preciseness will basically increase. Like you will be ultimately multiplying something with 2 to the power minus 19, which is really small value. So you are going towards a real value representation more precisely. However, since you only has 2 bit to play in the exponent field, your representation capacity, how much range you can represent, will severely decrease, right? So that means it becomes an architectural decision point that how much to be given for fractions, how many bits are to be allocated for the fractions, and how much bit has to be allocated for the exponent. So to resolve these different ideas and different opinion of how much to be allocated for the fractions and how much to be allocated for the exponent, IEEE 754 is a standard representation for all computing systems throughout the world that has been adopted by everyone. Okay, so this is a 32-bit representation with slightly different understanding of the fraction and the exponent part. Okay, so its most significant bit is allocated as a sign bit. Means if that bit is 0, it's a positive value. If that bit is 1, it's a negative value. And then next MSB side 8 bit has been allocated for the exponent, but this is a special type of exponent value calculation I'll explain. And rest 23 bit is a fraction. Now, how we are going to calculate the value, okay, or how are going to operate, basically what is the target representation become from this format, okay. So it, in a nutshell, it is saying that it's minus 1 to the power s. So this value you can well imagine, if s is 0, this value is positive 1, it's a positive, then rest of them, whatever you multiply that value, it's a positive. And if s is 1, then minus 1 to the power 1 is negative 1 minus 1. You multiplied some positive value with that, it becomes a negative value. So that's why this bit, the MSB 31 bit of this 32 bit representation represents a sign of the value. This is how, okay. And then it is 1 plus f, okay. So what it means, the fraction, it basically assume it's 0 point that fraction bit pattern, 0 point, then after that 23 bit of fraction, and it adds with 1. That means ultimately you're representing 1 dot some fractional bit pattern, and you multiply that with 2 to the power e minus 127. So e here basically is an unsigned value, okay, 8 bit. So that means its range is from 0 to 255, and we are doing the power of 2 as e minus 127. This is called a biased exponent representation with a constant bias of 127. That means if e is 0, your power of 2 is 2 to the power of 2 is minus 127. If e is 255, then your power of 2 is 128. Yeah, plus 128. So this is what we, how we do a fractional representation. And magnitude range, the smallest we can represent almost like 2 into 10 to the power minus 38 range, and highest magnitude can be almost 2 into 10 to the power 38. So E representation is a computing representation for 10 to the power some value. So the smallest one is 2 multiplied by 10 to the power minus 38, and highest magnitude I can do almost like 2 multiplied by 10 to the power 38. This range is way beyond integer representation of 32 bit, which is almost like 4.3 e to the power minus 9, like in terms of integer, if you think of for the unsigned value, right? So so this is a huge range we are talking of, and let me show you an example of how we are, like, from a bit pattern, how we are going to like convert it into the binary bit pattern. At this point, let me pull up my notepad to give you an example of 32-bit floating point. Let's say you get a 32-bit hex pattern like this for some, with some operations in the MIPS, and let's see what decimal value it represents, right? So if we convert this into 32-bit pattern, it will be something like this: 1110. 1110 is basically 8 plus 4, 12, plus 2, 14. 14 is 10 is A, 11 is B, 12 is C, 14 is D. So this is 1110, then 30011, and another 1110 is D, and then 5 is 0101, and 1100 is C, which is 12, and 00000000. So this is your 32-bit, right? So let's make that 32-bit, And now IEEE format says that your first bit is a sign, MSB is a sign bit. So this is 1, so it has to be going to be a negative. And then then we take 8 bit from here. This 4, 8, right? This is 8 bit. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the exponent. All right, so this is sign, this is my exponent, and this is my fraction. So fraction now, what fraction in a normalized form we are doing, we said it's 1 plus f, okay? So which basically we can imagine something like this, 0 dot this bit pattern with 1, you add them up, okay, and you get 1 dot this, right? So that's what is meant by your 1 plus f. So this fraction bit pattern is assumed to be 0 dot some fraction, and we always assume there is a 1 on top of that to make it a normalized representation. So this is my fraction, and then how about the exponent? Now exponent is equals or E, right, equals, now this is unsigned value, this is 8-bit unsigned value, which is basically we are talking about 1 1 0 0 0 1 1 1, okay. So this is your 8 1 2 4 8 16 32 64 128. So we are talking about 128 plus 64 plus 0 plus 0, 32 16, and then 0 8, then 4 2 1, right? So this is your exponent bit pattern corresponding unsigned value represent minus 127, okay. So this will give you plus 1, 128 minus 127 is 1, this is like kind of 1 plus 64 plus 4 to 7, 7, so this is basically we are talking about 8, and we are talking about 72 here, okay. So what it means is really this representation is telling me that this is a representation like a negative, then you shift the floating point 72 times, which becomes like 1, it will consume all these 23 bit in a binary, right? So this is 24 bit, right? Yeah, 24 bit together, and then 72 minus 23, which is 72 minus 23, how much it is? 72 minus 23 is, so 23 we already shifted. Now we need to append like another 49, right? 49 zeros after that. 23, yeah, there's 49 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Oh, 49. Okay. So this is your value. Remember that, okay, optional your floating point right here and followed by a 0. Doesn't matter. So this is a positive non-fraction value, and which is a huge value, right? Which represent more than what it can be done with a 32-bit representation. So your range is huge there, right? And let's say if we want to do another example, right? Let's say I want to play with this guy more. Let's say another example. Okay, so let's take this same bit pattern. Okay, but we'll just change it. So this is example 2. Okay, same bit pattern from this thing. Let's say we came up with something like okay, something like this. Yeah, something like this. Why not? Another example. Or okay, let me give you other way where it actually represent a fraction number. Okay, so that would be more like 0, 1, 1, 1, 1, 0, 0, let's say. Okay, so here in this case my exponent will be something like 64 plus 0 plus 64 plus 32 plus 16, 0, 64, 32, 16, 8. 2-bit, 4-bit. Oh, we are missing one here, right? Okay, here, now it makes sense. 64, 32, 16, 8, then 0 plus 0 plus 0. Okay, minus 127, which is mostly equals, this is 24, 16 plus 8, which is 24, plus 32, which is 64 plus 32 plus 24, minus 127, which is mostly equal to 64 plus 656 minus 127, which is almost like 120 minus 127, which is minus 7, right? So that means my fraction part was this, right? My fraction part was this. That means my original value, or n, is we are representing. So here this was something like minus some big values. Now here we are trying to represent, we need to shift the floating point 7 part. So that will be 0.123456. So this becomes your target value now. With just an exponent change, it becomes a fraction, small fraction value, and we can compute that as well. So this is what we meant by this, what we understand by this IEEE format.